Okay, next speaker, Susanne Hilger.
Okay, thank you for being here. Thanks to David for trying to convince me that it was a good training for me. Okay, I'm a PhD student together with Stefan Müller in Bonn, and he started together with Kotecky and Stefan Adams a project where they built up this Renormalisation Group Analysis, which was established by Gordon and Slade to their model of interest, which is a gradient model of non-convex interaction. And I think the project started quite a long time ago. Yes. Every now and then, Stefan Müller succeeds in convincing some students to work on the project, even though it means mainly working with unpublished papers. Okay. So what is the setting? We want to consider discrete gradient Gibbs measures. So we take a box lambda n in the discrete set T of side length L to the n, where L is some large number which is determined by the RG analysis. And we take periodic boundary conditions, so we just work on the torus. We consider fields phi from this box to R. So it's a continuous spin system. And the Hamiltonian is just given by this one here. So we take the sum over all x and lambda n, sum over all directions of some potential W, which depends on the discrete gradient of this field, plus some tilt U. So this U is an RD. It's so to speak, a boundary condition of the model. And so this model serves as a model for effective interfaces, and then this U is the tilt of the interface. And then, as usual, we build up a finite volume Gibbs measure, which is called gamma and beta U, which is of course given by so there's this normalization constant 1 over z, and then there's a Gibbs weight e to the minus beta HU, and some a priori weight, measure, where this partition function, well, it's just the integration over the Gibbs weight, and since the potential, since the Hamiltonian depends on the gradients, this is only well defined if we restrict ourselves to gradient fields, or equivalently to usual fields modulo constants, or would this done here to fields which live in this set chi n, which are fields which have vanishing average over the box. And then
the N is the big measure?
Yeah, it's just so this is the setting. And now the knowledge what we have about this model is is dictated by the choice of the potential W. So if W is strictly convex, then quite a lot is known. There's, for example, this result by Kotecky and S from '97. They show uniqueness of infinite volume gradient Gibbs measure for any tilt U. So they, more precisely, they say that for any fixed U, there is an infinite volume gradient Gibbs measure, which is ergodic and shift invariant, which has mean U. So this again shows this meaning of tilted interface. Furthermore, there's this result by Nadov and Spencer, '97. The scaling limit is a Gaussian-free field, and the covariance is just decay, as we expect that they decay if they have algebraic decay in the difference between A and B. This is just the result described by Delmotte and Dolce from 2005. Okay, so one now can think about what happens when W is not convex, but any non-convex potential or non-convex perturbation of something convex or so. And I just chose a few results in this case. The first one is by Biskup and Kotecky in 2007, where they it showed that for a special non-convex potential, or for a class of non-convex potentials, there's indeed a phase transition at some moderate temperature at 0 tilt. So there really something happens in this non-convex case. And I also want to mention that the surface tension can be non-strictly convex for a class of non-convex potentials, which is, for example, shown in this paper by Kotecky and S in 2014. I mean, there's much more in this paper, but just for this presentation, I just want to mention the surface tension. And then I want to mention this, these two papers by Kotecky and S and Stefan Müller, and the second one without Stefan Müller, where they show uniqueness of Gibbs measure, scaling to Gaussian-free field, and algebraic decay of covariances, just as in the case of convex potential, but now for non-convex perturbations of the convex potential and in high temperature regime. Kind of the other regime, the low temperature regime, is then which is studied by Adams, Kotecky and Müller, and this model I now want to present. So I call it an AKA model for Adams, Kotecky and Müller. So the potential here is it's just a quadratic one and a perturbation V. And on the following slide, I want to show the results on this model. Now in the following, I want to list the conditions on the parameters like L, U, and beta, and on this V here. So L should be large enough, U small enough, so this tilt should be small, and beta large enough. We are in the low temperature regime, and this perturbation V has to satisfy some conditions. In fact, it is kind of not allowed to destroy the convexity at the minimum. So V of so this function in 0 and the first derivative in 0 and the second derivative in 0 should be 0. Then there's a lower quadratic bound on the whole potential, and there's some condition on the higher derivative. So here the higher derivatives up to some order R star. And if we take the supreme or is smaller than some t, we take the limit t goes to infinity, and then this ratio here should tend to 0.
It looks a little strange to have omega less than or equal to 16.
Should be opposite, I mean.
You mean greater than or equal to 16, maybe, or not? Because I could take omega to be 0.
0, yeah.
Oh no. Yeah, sorry. But yeah. And we want to have some.
At least some.
Yeah,
At least some,
yeah,
yes.
sorry. Okay. Before stating the results, I just give the notation. I call a Gaussian measure mu with covariance CQ, like this here, whereas this covariance CQ is the inverse of the finite difference operator AQ, which is given by this here. So if this Q here is 0, then this is just the finite difference, the finite Laplacian. But we need some more flexibility here. We need this Q here later. Okay. So under these assumptions, then the result which appeared on Archive in 2016, Adams, Kotecky and Müller, is that the surface tension of this model is strictly convex in U. So the surface tension is just given by this formula here. And I think at that moment, yes, I want to also remark that at the moment they're working on an extension to activated fields instead of from the box to some R to the M for M greater or equal than 1. and to general finite range potentials instead of just nearest neighbor. And this is together with this B here stands for Buchholz Simon, which is another PhD student of Müller and Bonn. Okay, then under the same assumptions on these parameters and on V, one can show that the scaling limit is the Gaussian free field. So if we take some smooth, compactly supported F on the continuum torus, which has mean 0, and we define a scaled version of this smooth function, then there's Q, and here this Q now appears in the measure, such that the Laplace transform of this Gibbs measure here, of this finite volume Gibbs measure, tends to the Laplace transform of the Gaussian free field with covariance CQ. So this was my master thesis. And
What depends on you on the right hand side somehow?
there's no dependence on you, I think. But of course this only holds for I mean this only holds for U small. Yeah. So this is really based on
Q depends on you.
Q depends.
Q depends on U, yeah. Yeah, sorry, yeah. Q depends on the choice of U and beta and V. And L. But I don't know how to do this in U. And then
No, I mean, when you say there is Q, you mean that you find it, or there is an abstract argument which find it?
it's an implicit function theorem, so which says which gives the existence of one correct Q such that the method works.
So it's something which satisfies some conditions, some implicit relation.
But I mean, it must be small enough such that the measure is really a Gaussian. Yeah, but I don't know if we.
No, the Q. I mean,
Yeah.
The Q is
do you have an
constructed.
equation for Q?
No.
No, I mean even a relation. I mean something which constrain, because you say it's satisfying implicit function theorem. So
Yeah, it comes out of an implicit functions theorem, but
it's the fixed point of something.
yeah.
Okay. Yeah. So you have a relation for Q.
But relation is complicated because
Yeah.
this is Renormalisation Group.
Okay.
But actually still, in fact, you could actually calculate Q in perturbation theory from your relation, I think.
I mean, perturbation theory is kind of difficult here, isn't it?
Well, we
Because
can
this
argue
V
about
is-
it afterwards. But,
Yeah.
I think it is actually constructed in the sense that you could find Q. That's my belief.
Okay, and then in my PhD thesis, I did minor changes, like there's some, in the original paper here, there's some subsequence in here, and I removed the subsequence. Also here, there was a subsequence in this limit. This can be removed. I did that, and furthermore, I attacked the two-point correlation function under this finite volume Gibbs measure, and I found that that it just behaves as the covariance of the Gaussian free field with this covariance CQ here, with the same Q as above, with some corrections. So there's one correction which vanishes when the box tends to set D, n goes to infinity, since it's at constant in 0, 1, and there's a higher order correction in the distance a minus b. So this here has decay 1 over a minus b up to d, and so this is in this sense this is a higher order correction. So this gives really the algebraic decay as it is expected. And yeah, unfortunately I wrote this up based on this unpublished new version. I hope something happens soon. Okay, Now I want to get some really very few details of the proof. And I want to start, so this theorem here of Adams, Kotecky and Müller is based on our Renormalisation Group Analysis, and they managed to give a really useful representation of this partition function, and this I will give a sketch on that in the following slides. So at first we do some preparation of the partition function, which are really not hard, so I will go very quickly through this, and I will cheat on many places. Okay, first of all, when we insert the potential we choose, then it just looks like this. We have this quadratic part with this u in here, with this tilt, and we have the non-convex, the perturbation. Now we put out this part which does not depend on the field phi, and what else do we do? I denote this part here just by this finite difference operator A0. Then I do the Meyer expansion, which David explained us 2 or so weeks before. So I pull down this sum over all x, becomes a product, and I put in -1 + 1. This part here I call it curly k, gradient phi of x, and then I expand this product, which then gives the sum over all polymers in the torus, in the box. And then this here only depends on this polymer x. And then there's, of course, also a product of all x in the complement set of 1, but it just vanishes. And then I did some further stuff here. I changed A0 to AQ, which then I wrote it as Gaussian measure here, which implies the appearance of the partition function in front of the integral. And we have this corrective term here. So this is just exactly the part which we introduce here in order to get this measure.
I see. So the part with the q cancels something inside the mu.
Counter.
Yeah.
Counter term.
Yeah, it's exactly what comes here. And now we split the contribution, so we take also down the sum here to a product, and we split contributions of this term to this part here and to the complement, and this part involving this curly k we call k0, and the remaining we call it just h0. So h0 is really just this here. And this already is the separation into the irrelevant part and the relevant direction of the renormalisation group. Okay.
Dobrushin was always saying that this minus in E2 minus H is the only thing we have common with physics.
So you're arguing that there's
So
no
I know that Stefan Müller likes to put plus there, but I am somehow I do not like it at all.
Sorry. Okay, then I go very quick through the ideas of the shear analysis. The first step is the finite range decomposition. So it's really very similar to what Gordon explained to us in the first week of September. Finite range decomposition goes as follows. So our covariance CQ can be decomposed into these covariances, which have this nice finite range property, and that it is constant outside of boxes of side length L to the k. So we have this box lambda n of side length L to the n, and kind of we divide it into smaller boxes which have side length L to the k at each step. And we have some smoothness in this x here, and also in q. So the difference to what David and Gordon do is that we have no mass. It's a massless, massless model, and we have this additional dependence on this Q. Okay. Then we can use this decomposition to integrate out step by step, which gives us then a flow HKKK, where we carefully split the relevant part and the irrelevant part, and they live on increasing polymers at scale k. So polymers, I mean these blocks of cycling L to the k. And then there's this big issue of finding the correct norms to show some contractivity of this irrelevant part and smoothness. So I will leave this completely out of this presentation here. Okay, and then there's the first, in our case, the first big implicit function theorem, which states that for any Q and curly k is small enough, the flow exists and is, in fact, which is quite important for us, is smooth in this Q and curly k. It starts at the correct initial data. It's what I prepared on the slide before. It's really this one. Well, and we have nice convergence properties. Unfortunately, this flow here, so it has the right K0, but H0 is just anything. But we want.
Because
That's the
the
sensor.
right, the black box.
So the point here is that when you say the flow exists, it's a globe exists for all k. That's what you mean, right? Yeah.
For all curly k and for all Q, and it depends smoothly on these.
And you do not need terribly small Q. I mean, up to 1/2, in some norm diameter 1/2 or something.
Very
like
good.
that.
But where does it start from, the flow?
The initial condition k0.
And kind of we follow the flow of the irrelevant direction forward.
And what's H0 is that you just wrote there?
Sorry?
H0 is over there.
Yeah, but it
H0
comes.
is what the implicit function theorem finds, right?
So at the moment H0 does so it's anything, and we but since everything depends smoothly on Q, we can and on K, we can use a second implicit function theorem, which gives us really the correct H0 with this Q in here and not so this E here kind of
That's a function.
which depends on this curly K. Yeah, and then we can we can try to find a fixed point. So say this H0 depends on Q and this curly K, and the fixed point then should give us this really is the same. So this is the small addition which is needed here.
So one way of saying this then is that the interaction goes away completely, and H0 is the term which expresses the long-range behavior of the model.
Yeah, exactly.
There's no relevant direction on this
Yes,
because of the gradient.
it's completely.
There's one marginal as well, Q marginals.
Yeah.
Nothing to find, Joe.
Well, if you want to hit 0, like that it's fine-tuned, just like the wave function renormalization is fine-tuned in
Okay.
544. You only fine-tune it so that you have the
Yeah,
right
but
factors.
it's much harder in this case because you have to find this matrix Q.
Yeah, that's right. It's a matrix. It's not. So there's D margin.
I know it in finite volume version, and in finite volume it would be that somehow you start with some H0 and you want that Hn is exactly 0.
That's right.
Yeah. And this means that you have to choose Q.
Yeah, even if it was relevant, you would have
you are able to fine-tune Q in such a way that Hn is 0. Yeah? And this is the version where you go to infinity, so it goes to somehow it disappears in infinity. But you can fine-tune this Q in such a way that you are getting this.
Okay, the representation which one gets out of this renormalisation group analysis is as follows. I just want to repeat the partition function. We wrote it like this here, this EH0 and K0 and some prefactors. And we additionally we include an external field G now to just write down the generating function. So I really just put in this exponential part here, and this can be computed to just be this exponential to 1/2 G CQG, and then we have the flow which we understood, but just evaluated at an additional external field. And the result is the following. So there are just these prefactors, but this integral here we can follow the flow, and we end up with e to the hn plus kn. So at really the last scale, if k is n, then there's just one single block left, and this is shown here by only these two terms. And we have this input CQG of this external field. And this part here converges to 0 if this input G here is nice enough, whatever this means. And on my last slide, I want to give the scope and limitations of this theorem here, of this representation. So here's it again. Now, if we choose G equals to 0, this is absolutely nice enough. Then we can just analyze the surface tension. So we can just take the logarithm of this stuff. We divide by the volume of the box and take the limit n goes to infinity. And then what remains is mainly just this part here, u squared, which is surely strictly convex. Now, if we take G equals to this Fn, which I introduced before, which is this nicely scaled version of the smooth, compactly supported function, then one can compute the scaling limit. So this is nice enough in this sense here. But what now about the covariance? Well, the covariance can be computed as derivatives of the generating function, where we have this input here, exponential of s gradient phi in A plus t gradient phi of B. Well, one could think that one can choose as G here, something like this, s times the gradient, a joint gradient.
Shouldn't you take logarithm of this integral?
Oh, sorry, yes, oh my god, yeah. So here is the logarithm. Yeah, then we have the okay, if we choose G like this, then we are exactly in this shape of so we have exactly this form here. Well, but unfortunately this is not nice enough for this formula here. And so we have to do something else, and what is this? If instead we follow the flow of observables, which means that we put this into this flow here of H0 and K0, so we extend H0 and K0 and the whole flow, and follow the observables step by step. And fortunately, this is also done by Gordon and David, so that I could just copy their method. Yeah. And with this, I want to end, and thank you for your attention.
Any more questions?
Any question? What is the meaning of this tilt U? the tilt that we introduced?
Yeah, so this is a model for the for an effective interface where this field phi is the height of the interface. And like this, right? This is phi of x for an x here. And yeah, and then the tilt is kind of the tilt of this interface. And the hope is that, or which is the fact which is driven by Kotecky and S in the case of convex potential is that in the infinite volume limit, we really get for each tilt, we really get a in the mean we get a plane which has done this tilt.
You could think of taking a crystal again, like that. And then
Oh yeah, you can see his foot.
looking at an interface force. Right. Okay, thank you very much.